Hello, AP Chemistry students. How are you today? I hope you're having a fantastic day. And I hope that today's video is the best one yet in the AP Chemistry video series. So let's go. We are looking at page 4, and we're talking about de Broglie's equation. The idea is pretty simple. So we talked about light, and that light has both wave-like properties and particle-like properties. And that's that whole photons business. So if you have photons of the appropriate energy, and they hit the surface of a metal, they may be able to eject electrons. And that is very particle-like. So today's question is the opposite true? Can you have an object that's moving, display both particle-like behavior, because it is a particle, and have a wavelength? And the answer is yes. And that's the essence of de Broglie's equation and de Broglie's work. So de Broglie's equation, first of all, you never have to memorize this because it will always be given. You see a lot of things that are familiar. So you got wavelength. This is the wavelength of some moving object, okay, like an electron or a baseball, okay? And then H is Planck's constant, same number. Joules times seconds is the usual units, but we're going to use alternate units for this. And basically what we did is we took a joule and just kind of broke down what a joule was. And a joule is a kilogram times meters squared over second squared. And if you put that with seconds and simplify, you end up with these units. We're going to use these today. So what that means is that this mass, it has to be in kilograms because we want it to cancel out with these kilograms. So that's fine, but that is something that students often forget. So be careful with that. And V might have thought was frequency, but it's actually velocity. It's how fast is that object traveling. All right, so let's go ahead and give it a try. So this first question is actually about a photon of red light and what mass would it have? Okay. Well, let's go ahead and tackle that. So I'm going to rearrange the formula a little bit. So mass equals Planck's constant divided by wavelength times the velocity. Okay, and I'm going to go ahead and pop that Planck's constant in, times 10 to the negative 34th. I'm going to use those alternate units, which are kilograms times meters squared over seconds. And then how about the wavelength? So it's 650 nanometers. So you will have to convert that to meters. Okay, and I'm going to use 1 times 10 to the 9th nanometers equals 1 meter, but you can do the opposite. That 1 nanometer equals 1 times 10 to the negative 9th meters. However you like best is fine. And then multiply it by the velocity. It doesn't say the velocity because it's a photon of red light. That's electromagnetic radiation, which always travels the speed of light. So that's its velocity. Okay? So the reason why I'm really spelling this out is because I want you to see how the units cross out. So let's see here. So of course the nanometers are gone. We have this meters and we have this meters. These two together will cancel out with the meter squared. And then this second cancels out with seconds. And the only units left are kilograms, which is great. So you guys can go ahead and punch that in. And as it turns out, the answer should come out to about 3.4 times 10 to the negative 36 kilograms. So we're talking about the mass of that photon. Well, it's a pretty small mass, and I'm sure you're not surprised to see that. So it's not very measurable. This is kind of more of a theoretical prediction. So commentary, how significant is this mass? Well, you know, photons do have mass, but not much. Have mass, but not much. So therefore, you know, it's not something that we're going to be able to mass out on a scale or something like that. Okay, but photons energy does have mass. All right, so you can do the exact same thing, but this time with a normal everyday moving object like a tennis ball. So it says calculate the wavelength in meters of a fast-served tennis ball, 0.060 kilograms, traveling at 62 meters per second, about 140 miles per hour. Okay, is that fast? I think it is. Okay, and I would suggest that you guys work through it until you get this answer. Make sure you understand how it works, and there's some practice with OWL as well. Okay, but if you do work through it and you get this answer of 10 to the minus 34th meters, what's your commentary on that? How significant is a wavelength that's 10 to the negative 34th meters? So a tennis ball does have a wavelength. Has a wavelength, but way too short to be significant at all. Okay? So far, we've done 2 examples. In either case, the mass, the wavelength is not significant. So why would we care about this? Okay, so that's a good question. All right, so the take-home message is this. is that photons have pretty insignificant mass property, and big objects like tennis balls have pretty insignificant wavelengths. But what if you can kind of find something that's sort of in the middle? So the perfect thing is like an electron. Okay, so an electron has a really small mass and it's traveling really fast. And because of that, it actually has a wavelength that can be measurable. Okay, so in your notes, it says that it has a wavelength that's in the X-ray range. X-ray range. Okay, and that's pretty significant because that means you can measure the mass of an electron, and you can also measure the wavelength of an electron because it's in the X-ray range. Okay, and there's some ways we can do experiments to prove this. So the classic experiment is called diffraction experiments. Okay, and you see these three graphics, and they sort of show us the significance of an electron having a wavelength. So this first graphic right here is basically we have this electron source. So this little whatever is just shooting electrons really fast, and you have these slits that are in some kind of piece of plastic. Okay, and if electrons truly just behaved like matter and like an object, then those electrons, some of them would get through the slits, and you would see marks on the other side, and there'd be some kind of detector that could pick that up. Now, if we were talking about wave-like behavior, then it would look very different because when the waves go through those slits, it's kind of like when you throw a bunch of rocks in the water and you see all these waves and some of them like add to each other and some of them cancel each other out. So with all those waves interfering and canceling each other out, you would see a very different pattern. You would see the detector would pick up marks in these places, okay, wherever the waves kind of added together versus canceled each other out. So that's if something behaved like a wave. Well, what you see with electrons is very much a mixture of both. So you shoot those electrons, they go through the slits, but instead of just seeing the marks where like the object known as an electron would hit, you definitely see what would indicate that those electrons are behaving like waves. So that's pretty cool. So this is basically called a diffraction experiment. Okay, and we're going to talk about that a little bit more as you'll see in class. Long story short, if you've ever heard of an electron microscope, okay, that's basically the premise of how they work, because instead of relying on just light to bounce off objects and to see things that are really small, now you can rely on electrons behaving and having that wave-like behavior and being in the X-ray, which is a much smaller wavelength than normal light, and you can pick up some pretty cool images. So these are just some of my favorites, mainly because, it's a spider. This one right here, we're actually picking up like ice, water in ice form and solid form, the beautiful crystal known as ice. And you can pick up some detail that you can never pick up with a normal microscope. So basic premise is without, you guys are going to practice using this formula. And the basic idea is, do you understand the relationships? So basically, the higher the mass, what's that going to do to the wavelength? The shorter the wavelength is going to get. Okay? And if that mass is too big, that wavelength is going to be way too small to be notable. And likewise, it also has to do with the speed. Okay, so the faster the speed gets, faster it's moving. Okay, that's going to cause that wavelength to be really short too. So if you can understand the relationships that are in here, then life is good. All right, well, thank you so much for listening, and continue having a fantastic day. And thank you for listening.